Alrighty. So you know how they're kind of adding all these different sports to the Olympics every year, it seems? Why do you suppose they're not adding a sun-tanning category? I mean, I would have thought that they might add sun-tanning to the Olympic sports.
Why is that?
Yes?
Oh, well, my mom used to own a sun-tanning, like,
Thanks, Jeff.
salon. Like a suntan place, right?
Okay.
Tanning beds and stuff. And frankly, the government doesn't really like tanning. It's
Really?
bad for you.
It gives you cancer.
Yeah, not really.
I suppose.
It really doesn't, but like there's a bunch of regulations for it, and like it's kind of a dying industry.
Okay.
Dying industry.
Yes, Keegan.
You ever watch, I forget which Rocky movie it is, but it's the one with the guy that looks like Kristaps Porzingis? You know what I'm talking about?
I have no idea who that
The
is.
fourth one, Rocky 4 or Rocky 5, either or, it doesn't matter. Anyways, if you've seen that guy, you know he looks like a complete idiot, especially with the tan he's got. There's no way that's his real skin color. And
Dolph Lundgren, the main guy, the big Russian guy?
Yeah, the main Russian guy. He's
That's
like,
definitely-
Isn't he like super white?
he's like orange tan.
He's really
He's
not.
literally orange tan.
He's Russian. He's like pale.
Exactly, that's the point. But he's orange tan, and he's supposed to be Russian.
No, he's not orange.
Oh.
Search it up. Anyways.
Yeah, you can see if it's still around there
He's like
somewhere.
Drago.
Anybody see a binder over there?
No.
Yeah, if I find it, I'll put it in the lost and found for you for tomorrow.
Anyways, the dude's literally orange
So-
tan.
Okay.
Oh, we can't have that again. He's
So-
too stupid.
Let's get back to the original question. Why do you suppose it is that the Olympics do not have a suntanning category? And the answer is because you would never get anything better than bronze.
Oh my god.
Okay.
Wait, say it again?
Because you would never be able to do better than bronze. Because when you tan, you get darker bronze. All right. Last physics class liked that
I
one.
named my pet Rocky.
What about
I kind of ruined it with like
I
the
just
actual
said it.
genuine answer.
That's okay.
That's
okay.
That
The
was a joke, right?
why do you suppose it is that candles oftentimes just quit work for no reason at all? Yeah, they just burn themselves out. All right. Boy, we are off to a roaring start here, aren't we?
Yeah, honestly.
Okay. Let's take a look at the question. Hopefully you got it written down. We've got this picture here, and we've got this mass sitting on the incline. The velocity is equal to 0. That means there must be some friction there keeping it in place. And you can see the angle in the corner of the triangle there. So the question is, what happens to the following forces as the angle increases? So, we've got 4 or 5 forces that we're considering here. First is friction. So as this angle goes up, what do you suppose happens to the force of static friction?
Goes up.
Yeah, it's going to go up because it needs to be stronger to keep this mass from sliding down. What do you suppose happens to the normal force? This is a tricky one. Think of yourself as being the table on this. Think of yourself as being the flat surface. As this angle goes up, are you going to have to exert more or less effort on this box? A little bit less, actually. That's okay. Because, like, as this angle goes greater and greater and greater, the surface itself is going to be exerting less and less force on the object. Because, like, by the time you get vertical, this isn't going to be pushing on it at all. So, yeah, your normal force will actually decrease as the angle grows. Force of gravity, how's that going to change? Oh, you got to answer this one. It's going to stay the same, absolutely. Force of gravity in the x direction, so that would be the force of gravity acting along the surface. Does it get bigger or smaller?
Bigger.
That's absolutely right. And the reason for that is because as your angle grows, more of the force that's trying to pull it down is going in the x direction. Because the x direction is simply parallel with the surface. So as that surface gets more vertical, you've got more of that gravity actively pulling it down in that direction. So you can probably guess what's going to happen to the y direction. It's going to get smaller because as that angle grows and as your normal force would get less and less, your force of gravity in the y direction would get less and less too. So I'll just answer these with arrows for the folks at home. That normal force is a tricky one. So these would be your answers. Force of friction would go up, normal force down, force of gravity would be equal, force of gravity in the x direction would increase, and in the y direction it would decrease. All right, the main event for today is worksheet number 3. Want to make sure that we're okay on this stuff, so hopefully we can get through 3 problems today. That's our goal. We'll start with number 2, and then we'll see if we can plow through numbers 7 and 8. Talk a little bit about the Kardashians.
Yes.
So number 2.
I love keeping up with them.
Why are they so fast?
They're so fast.
Fast. I can never catch up.
Oh, I get it. That's pretty good.
I don't like you.
That wasn't even supposed to be like good.
Oh, okay. Well, I like you again.
So for number
You wanna
2,
kiss me?
No, not here.
yes.
No.
Same
Mr.
bathroom
Hathaway,
after
Maggie's
class.
bathroom, and he wants to too.
Just one person at a time.
What? Excuse me.
So, boy, this really is turning into an interesting class,
oh,
isn't
God,
it?
I'm coming.
Video here.
Oh, it is.
Oh, God. I didn't mean it.
Vegan. I know we're in physics, but you want to practice.
Okay, here we go. So let's take a look at our force diagram. We've got gravity going down on number 2. We've also got an applied force that is going down in this direction, and because our angle is 20 degrees with respect to the horizontal coming in, it's going to be the same thing coming out of our dot. So 20 degrees is going to be our angle right there. Of course, it is on a flat surface, so there's going to be a normal force. Do you think that normal force will be bigger or smaller than gravity for this condition where we're kind of pushing down on the object? It's going to be more, exactly. Because if you think of yourself as the table, if you're pushing down on the object, not only do you have to push up for however heavy the mass is, but you're also compensating for the amount of push that the person's putting down on it. So the normal force is going to be bigger than gravity in this case. And that is our force diagram for letter A. Letter B says, determine the x component of the applied force. So here's the thing. When I was looking around at some of your question 2s on the homework, it looked like some folks were still like rotating their x and y axes. Keep in mind that that's the sort of thing we only do when we're sitting on an incline, like that over there, or like problem 1 or problem 4. Otherwise, we keep our axes straight up, down, left, right, and this is no different. So if we're looking for the x component of the applied force, what I'm looking for, really, is the amount of this force that's headed in the x direction. So I'll call it FAX, applied force in the x direction. Because when you're pushing down on that object, part of that force is going to the right, part of that force is going down. So for this, we want to figure out exactly how much of that force is acting to the right. Now we do know that the applied force here is 25 newtons. So we have that going for us. If we were thinking about the y direction, it would be down here. So, are we able to figure out the applied force in the x direction? Answer is yes. So we've got ourselves a little triangle here. The hypotenuse would be 25. That's our applied force. Suppose I should label that. And we know the angle's 20 degrees. We're looking for the adjacent side here. So if we're looking for the adjacent side, are we going to use sine or cosine to figure that out? Cosine. 100% right on the money. the cosine of 20 degrees is equal to adjacent, which is FAX, over hypotenuse, which is 25. And so with that, we can find FAX by multiplying both sides by 25. And as long as you put this into your calculator correctly, which would need to be in degree mode, you're going to get an applied force in the x direction of 23.5. And that's how you do letter B. Letter C. What is the acceleration of the block? So let's imagine that we had friction here. There is no friction, but if we did have friction going this way, then the equation we would use to get the acceleration would be applied force minus friction equals ma. But because there's no friction, the equation simply boils down to this. Applied force in the x direction equals ma. So I say this because F equals ma is a wonderful thing, but you got to realize that this force is your overall net force. So if we had another force in the x direction going left, we'd have to subtract that from this when we set it equal to ma. But we don't have it, so it's nice and simple like this. So if I want to figure out the acceleration then, I just got to divide both sides by m. And we have both of those numbers. Applied force we found in letter B. And the mass is given, that is 5. And when you do the math, you'll get 4.7 meters per second squared, and that would be your acceleration here. Questions so far? Why is it that when I calculated this acceleration, that I looked at the horizontal forces instead of the vertical ones? Why didn't I go normal force minus applied in the y direction minus force of gravity equals ma to calculate acceleration? Why didn't I do that? The reason is simply, I'm not accelerating in the vertical direction. The block is accelerating horizontally on a horizontal table. So the forces that you need to consider when you're figuring that acceleration out are just the horizontal ones. That's why I'm only looking at applied force in the x direction here. Okay, letter D. What is the normal force on the block? This is going to take a little bit of doing. So, in order to figure out what's going on vertically here, we've got 3 different vertical forces. We've got normal force, force of gravity, and applied force in the y direction. So, in order to figure out my normal force, we start the exact same way we would start any problem in this section, and that's with a force equation. So, for a force equation that's looking vertical, we've got normal force up, and that's the only force going up. We've got 2 going down. We've got applied force in the y direction, and we've got gravity. Now, normally, I would set this equal to ma in this section. But is there any vertical acceleration going on here? No, absolutely not. Because it's accelerating horizontally on a table. It's not accelerating up and down. So that means vertically my acceleration is 0. So we can set this whole side equal to 0 then. Because 0 times whatever the mass is going to be 0. Questions on where this comes from? Okay. So if we're going to find normal force, I just got to isolate it. So I'm going to put these 2 guys on the other side. That makes them positive. So there we go. Now I just got to find force of gravity and applied force in the y direction, and then I will have my normal force when I add them together. So force of gravity is easy enough. That's just mg. So my mass is 5. Absolutely, times 9.8. So that'll be equal to 49 newtons. That is the force of gravity. Applied force in the y direction, that's over here. This is the opposite side of our triangle. So that means we're going to be using a sine function to figure it out. Bless you. So the sine of our angle is equal to opposite FAY divided by the hypotenuse, which is 25. So if I want to solve for the applied force in the y direction, I just multiply both sides by 25. And if we calculate that out on my super expensive calculator that I've had since 5th grade, 8.5? Yeah, 8.55 is what I got for that. Yep. So, we've got our two numbers. 49 newtons would go in there. 8.55 would go in there. Add them together, and you'll get your final answer. And when you round your final answer to 3 digits, you get 57.6. Again, if you want to go beyond 3 digits, that's fine. But yeah. And that's number 2. Questions on this?
So how do you know when to use sine, cos, or...
Yeah, sine and cosine are the main two that we're dealing with in this. And you're going to use sine if you're dealing with the opposite side that you want to find, because sine is opposite over hypotenuse. And you'll be using cosine if you're looking for the adjacent side, because that's adjacent over hypotenuse. And you almost always will have the hypotenuse. Okay, so that's number 2, which is pretty similar to number 3. And we did number 4 and 5 and 6, so let's jump to number 7. This is the new stuff. All right. So we've got the Kardashians, and they're all in a car. That car is parked 10 meters from the edge of a cliff, and when you take all the mass into account, the Kardashians plus the car, you get 1,000 kilograms. I noticed this, and I want to try a physics experiment, so I tie one end of the rope to the bumper of the car and the other to a 50-kilogram rock. Then I release the rock over the edge of the cliff so that the car, which is in neutral, accelerates towards the edge. Friction is negligible here, so obviously that means that the car, plus the Kardashians, will be going towards the edge of the cliff.
No.
I know, right?
No, we have to stop it now.
I have to try and keep this one updated. It used to be Jersey Shore, but I think I changed it a few years ago. So if you think I ought to change it to something else, let me know. So, letter A, clearly draw and label a force diagram for the car and the rock.
You didn't have it as Justin Bieber ever?
No, I haven't.
That would still be funny to this
Maybe
day.
you think he's more annoying than the Kardashians?
No, I mean, he's any of the 3 you just named would still be funny to this day.
Okay. I should just have a list of random people in the car.
Yeah. Yeah, just like make like an entire paragraph just in the people in the car.
Right.
Ranger from like Justin Bieber to like Spider-Man.
Alright, so here's our car, plus Kardashians. It's got gravity going down, it's got a normal force going up, and most importantly, it's got a tension force to the right. We'll say it's to the right, there's no picture on this, but we'll say it's going to the right there. And then, of course, I'll label this K for the Kardashian car. And then we've got the rock that's over the edge. We'll label that R. And that rock has a force of gravity down, and it's got a tension force up, and those are the only two forces acting on that rock. So, that is step 1, and that is part A for number 7. Letter B, what is the acceleration of the car towards the edge of the cliff? So, when we're figuring things out with problems like this, and number 7, if you're looking at it, would look very similar to number 6 on that picture. It's like having two masses, one on a table, and there's a string going across it over a pulley, and then you've got another mass that's hanging off of that table. It's the same situation here. So we solve it the exact same way. Now, step 1 in our 4-step process, if you remember, is to draw force diagrams. So we're done with that. Step 2 is to create force equations in the direction of each object's motion. So, for the Kardashians, what direction are they going, horizontally or vertically? Horizontally, at least in the beginning. Then horizontal forces are the only forces we have to consider here. So tension force is the only horizontal force that's acting. So that's going to be equal to MA. More specifically, the mass of the Kardashians in the car times their acceleration.
They're pretty heavy.
So that's MK. Yeah. For the rock, it is moving vertically. So we got to take its vertical forces into consideration. So when I'm making the force equation for this rock, what important point do I have to remember? Something about certain force coming first. Yeah. Whichever force is winning must come first in this force equation. So if this rock is accelerating down, that means gravity is winning that battle. So the force of gravity is going to come first in that equation. And that's what my equation would be for the rock. Questions on where either of these equations came from? Okay, so then step 3 is to isolate the tension forces in these. So it's already isolated there, so that's good to go. I have to isolate my tension force over here now. So what I'm going to do is take this, move it over there. That'll make tension force positive. And I'm going to take this product and move it over there. That'll make that product negative. Now, force of gravity is just mg. So that's the mass of the rock times g minus the mass of the rock times a, because we've moved that over. And that's going to be equal to my tension force. So now both equations are solving for tension force, and that's exactly where we wanted to be. So once we get here, it basically turns into a little math exercise. If this is equal to tension force, and this is equal to tension force, by definition, we can set those two things equal to each other. So the mass of the car and the Kardashians is 1,000 kilograms times A, and that, because it's equal to tension force, will be equal to this. So the mass of the rock is 50. G is 9.8. And again, the mass of the rock is 50. The acceleration is what we're looking for. And that's our little math equation. That's what all this boils down to now. We just have to solve for the A. So if I want to get these A's in a position so I can figure them out, I'm going to take this 50A and I'm going to shift it over here. So because that's negative, it would become positive when I move it over. So this will turn into 1050A. And 50 times 9.8 is 490. So now to solve for acceleration, I just divide both sides by 490. So 1050 divided by 490. Yeah, that sounds about right. Or, wait a minute, no, I said that wrong, yeah. It's actually 490 divided by 1050 to get the A by itself. I'm sorry. And yeah, that's absolutely correct. 0.467. Yes.
Yeah, he's arrested.
Yes. So there you go. Questions on where this comes from? Okay. So then the next part says, how long do the Kardashians have to apply the brakes before they go over the edge? So you're looking for a time here. And again, we're not really dealing with these equations in depth too much yet. The next chapter is when you're going to learn how to figure out which situations to use which equation in. But the equation that we would use here is this. As usual, we're starting at the 0 point, so original position is 0. Original velocity is nothing because they're starting from rest. So we've got x equals 1/2 at squared. Now it says that the cliff is 10 meters away, so our position would be 10 meters. Then we've got 1/2. The acceleration is what we're looking for, or no, we have the acceleration. We found that. Yeah. And then the time is what we're looking for here. So if I want to figure out time from this equation, I multiply both sides by 2 to get rid of the 1/2. I divide both sides by 0.467, and then that will be equal to t squared. So that's 42.8. And what do we got to do to get rid of the square? Square root both sides. So when we square root both sides, we're going to get our final answer, which is 6.54. Do you think they're going to hit the brakes before then? I doubt it. Okay. Let's see if we can plow... Well, any last questions here? Okay. We'll see if we can get through number 8 as well. 8 is pretty much the same story. It's just we've got a bit more complicated of a force equation for one of the masses. So let's jump into number 8. So like I mentioned before, the good part about all this is that you solve all these problems where you've got masses connected on a string in the same way. Step 1 is to do a force diagram. And for number 8, we've got 2 blocks, block A and block B. You can see block A is heavier. So the only forces acting on block A are tension force up and gravity down. So that's what your force diagram would look like for block A. For block B, it's got a string attached. So you've got tension force up and gravity down. So you have pretty much the same force diagram for both of those masses. And that's step 1. Step 2 is to create a force equation for each of those. So let's do that. So we've got block A and we've got block B. So Let's use a different color. So block A is the heavier one. So that means gravity is winning in that battle. Gravity is bigger than tension force. So the force equation for block A is going to be gravity minus tension equals ma. For block B, it's just going to be the same thing but flipped. Because block B is going up, the tension force is winning. So it's Ft minus Fg equals ma. And the little AB subscripts are just to help me remember that they correspond to those masses. So that's step 2. We're halfway done. Step 3 is to isolate the tension force in both equations. So if I want to do that here, I'd move tension force over there, making it positive. I'd move ma over there, making it negative. And force of gravity is just mg. So this is going to be mg minus ma equals tension force. And it's kind of the same story here, only now we're going to keep tension force right there, and I'm going to move force of gravity to the other side. And that makes force of gravity positive. And once again, now that we've got two equations that are both equal to tension force, by definition, we can set those two things equal to each other. So let's do that. Mass A is 5 kilograms. So 5 times G, 5 times 9.8, minus mass A, which is 5 times 8. And that's going to be equal to this version of tension force. Mass B is 2. Acceleration is what we're looking for. And 2 times 9.8. And once again, this boils down to a little itsy-bitsy math problem. So we want to get the A's together. So I'll shift this negative 5 over to the right, and that'll make it a positive 7A over here. And I'm going to take this and move it to the left. So that's what we have there. A little bit of math later. I get 29.4 over here equals 7A. So to get the A by itself, we divide both sides by 7, giving us a final acceleration of 4.2 meters per second squared. So even though number 8 looks more difficult and complicated compared to number 7, it's it's the exact same procedure. Okay, so then finally letter B, how long will it take for block A to fall 2 meters? Well, we're solving for time again. And we just got to use that same long x equation. Doesn't say anything about not starting at 0, so original position is 0. Starts from rest, so velocity is going to be equal to 0 to start. And we have our same thing here. X equals 1/2 at squared. Now we're looking at how long it takes to fall 2 meters. So this is 2 equals 1/2 times acceleration, 4.2, and t squared. So multiply both sides by 2 to get rid of this. Divide both sides by 4.2. So I got 0.952 equals t squared. And if I want to get the t without the square, I square root it. And I get 0.976. And that would be my final answer. So there you go. Feel free to check the answer key. It is posted online for some of those other questions on this worksheet. I will come around to grab this before you leave. And that's good for today.
Andrew.